Welcome to the second lecture of the SMT block. Today we will really talk about SMT. In the last lecture we talked again about SAT solving. This is the reason that SAT solving, practical SAT solving, is actually in the core of SMT solving, as we will see. But today we will really see what SMT is about. And in order to show you what SMT is about and what we can do with SMT, let's have a look at a small example. You know this maybe. This is a very popular puzzle, and it's called Magic Square, and the task is to arrange the numbers 9 to 9 in a 3 times 3 grid such that the sum of the numbers in each row, in each column, and in the both main diagonals give the same value. Okay, and we do not want to solve this by hand, but we want to encode this problem as an SMT formula and solve it with an SMT solver. Yeah, okay, and here I have an example how a solution can look like. We have these 9 fields, and in each of these 9 fields we put one of the numbers 1 to 9, and as this is a solution, we get the same sum for all rows, for all columns, and also for all the 2 diagonals, and this sum is 15. And yeah, so what do we have to do when we want to specify such a problem? Yeah, first of all, SAT solving is not very well suited to solve this kind of problem, because obviously we need to be able to deal with numbers, and in SAT we have only Boolean variables, and we also need to be able to do addition, so we need to sum up the numbers, and this we can also not easily do with SAT. In principle it's possible, but we would have to model an adder, and this becomes then very complicated for solving this small problem. So what we will do instead is we will use a logic which provides the handling of numbers. And yeah, we could use first order logic, what you have seen in the previous 2 models, but here the problem is that using first order logic is a bit of an overkill, because we just need to deal with numbers, but we do not need the other features provided by first order logic. And as a compromise, we have satisfiability modulo theories, SMT, which allows us to decide what kind of features should be supported by a solver. And we need numbers, so we choose a logic which provides us numbers as a background theory. Okay, so now assume we have a logic that can provide the necessary components we need to encode this problem. So how can we specify the problem? Yeah, first of all, we have to introduce some variables which represent the values of the fields. We have therefore 9 variables, and here in this small picture I showed how I assign the names to the fields. So we have here in the left upper corner F1, then we have F2, F3, and so on. And what is also important is that these variables may only take values between 1 and 9. Then we need a constraint that says that all of these formulas, all of these variables have a different value. So all variables are different. And then we need the sum constraints, saying that F1 plus F2 plus F3 is the same as F4 plus S5 plus S6 is the same as F7, F8, F7 plus F8 plus F9. And here I say these additions have the value S. I could in principle have put everything in one line and also replace the upper S here by these equations we have down here, but I think it's more readable when we split it, so I introduced the S. Yeah, I could even have written down the 8 equations in different lines. Yeah. I hope this is not confusing. Here in the first line we have the rows. In the second line we have the columns, and in the third line we have the diagonals. Yeah? So we have 1, 5, 9, 3, 5, 7. Yeah? The 1, 2, 3, for example, is a row. 1, 4, 7 is the first column here, and so on. I hope this scheme is clear. Yeah, and when we have formulated this set of constraints, then we have fully specified the problem, and then we can ask a solver, what should this S, what is the value of S, and how do we have to assign the variables f1 to f9 in order to get the required solution. Yeah, and this we can encode in SMT, and I will now show you how this looks in SMT lib2 format, which is the standard input format for SMT solvers. It's a bit, it looks a bit complicated at the first sight, but when you work a bit with it, then it becomes very natural, and this format is somehow a compromise between a format that is human readable and a format that is easy to process for computers. Yeah, so it's a bit, yeah, maybe yeah, it might require a bit of time to get used to it. But it's an extremely powerful format and language because it combines a lot of features, and some of them we will discuss in this course. So first of all, what we have to do is when we do an SMT encoding, we have to say which logic do we use. Yeah? So we tell the solver we need some features, and those that are not mentioned here, they are not considered. And this allows then the solver to make some assumptions and to use certain techniques for solving the formulas. And important is also that there are a lot of SMT solvers which are focusing on a specific background theory. For example, there are solvers which just focus on strings. There are some SMT solvers which focus on integers, on floats. There are some for bit vectors, arrays, and so on. Yeah, and there are also some solvers which provide a lot of, which support a lot of background theories. And a very famous solver is the solver C3, and I will put a link into the Moodle. And this solver supports a lot of background theories. It's a solver developed by Microsoft, and for our purposes it's very well suited. And there are also some web interfaces such that no installation is necessary, but if you want you can also download it, and there are binaries for different operating systems, so you can also use it locally on your computer. But in the demo I will do in a couple of minutes, I will use a web interface. Okay, so first of all we say which background theory and logics we use. We say we do not use any quantifiers, so it's quantifier free, which makes life, or the solver's life, much easier. And then we have linear integer arithmetic. Okay, so we restrict the kind of reasoning on the numbers to linear integer arithmetic. So we have integers, and we say that the formulas that we use, the equations and inequalities that we use, do not contain only linear expressions. Okay, and first of all we have to declare the variables, and we have the variables f1 to f9 and s, and we say they are just integers. Here we could also give the types of parameters. This is necessary if we would declare functions, but we just have constant symbols, and therefore we do not have to give any arguments here. Then we have to say some the restrictions about the values the variables may take, and constraints are started with the keyword assert. Maybe you know this from a programming language, where you also can add assertions which say that a certain point in the program execution some Boolean expression has to hold. Here we have a similar meaning of the assert statement, and the argument of the assert statement is a formula. It's a Boolean expression, and here we have a conjunction. This is starting with the keyword and we say f1 is larger or equal to 1 and smaller or equal to 9. Yeah? What you see here is that we do not have an infix notation where we have the operator in the middle, but we have first the operator and then the arguments. Yeah, so we have this prefix notation here, and for each of the variables we do one assertion. Assertions are connected by a logical AND. We could also have here in one assertions the other constraints here and merge it. But yeah, for readability I put it down. I wrote it down like that. Yeah, and then we have also to say that all of the 9 variables have a distinct value. For this I use the predefined predicate distinct, and assert distinct f1 to f9 is only true if all of the 9 variables have a distinct value. And finally we add the constraints that say how which say that all rows, columns and diagonals lead to the same sum. And here we define the S. We say that S equals the sum of f1, f2, f3. S equals also the sum of f4, f5 and f6 and so on. Yeah, and with this we say that all of these additions lead to the same result. When we have written down this, here with the semicolon we have a comment. We can do the solving. Solving is done with the command checksum, and if the formula is true we can also get a model which gives us the solution. And now I will switch to the web interface of C3 and we will have a look how this works in practice. Okay, so for this demo I use an online demonstrator of C3 here, and I have here an input field where I put the code which we prepared before. I copy this code into it, then I execute it, and what I get is indeed a solution. I get the information that S, or one solution where S is set to 15. This is similar as the solution we have seen on the slide in the beginning. And then I get values for F1 to F9. And what I see indeed is that all of the variables are distinct. I could now play around a bit with it and can say, okay, what would happen if I omit this distinct constraint? Then I ask for a different solution, and then I would get a solution where S is free and all of the other F variables take value 1. Okay, obviously this is a solution, but we violate the constraint that all variables, all fields have distinct values. Okay, so I put the distinct inside again. I could also ask if there is a solution that is different from 15. I say that S is not 15. Like that, so not S equals 15. And when I execute it now, then I get the information that there is no solution where S is different to 15. And I get also an error in line 44. And this error comes from the call of the get model, because I now call get model. I call the get model function on a formula that is unsatisfiable, and such a formula obviously does not have a model, and therefore it does not make sense to call get model. And therefore I get this error, model is not available. Okay, so there is no different solution than 15. This we have also now checked. And what I also wanted to show you is that we could merge these assertions here. For example, I could simply remove this one and put it like that. Let me see if I forgot something. Here I have to remove the parentheses, and then I have here a conjunction with 4 elements, and when I execute it, everything works as before. Yeah. Okay, so this was the first example I wanted to show you, and I have another one. The second example I would like to show you is a more serious one. It's a one from the context of verification, and the task is as follows. We are given this program middle here, which takes 3 integers as input, and it should return the number in the middle if we sort these 3 integers in ascending order. And the task is to find out if this program is always correct. And we could find this out by testing. So here I have a couple of test cases. So for example, if we give the arguments 1, 2, 3, then it returns 2. When we give 2, 3, 1, it returns 2. If we give 1, 2, 1, it returns 1, and so on. So it looks rather good. The problem is that testing is never complete, it's not exhaustive, and it could be that we overlook some case which leads to a problem. Yeah? So with testing, we cannot prove the correctness of the program. We can only show that it works for a certain input. And indeed, when you look at the code, it's not so difficult to see that there is a problem. If we use the test case 213, then the program returns 1. And this we do not want to have, and the question is, how can we avoid to overlook test cases? And here, logical formulas can help. We can encode the program as a logical formula. We can encode the specification as a logical formula, and then check if the program always conforms to the specification. And this we will now do with SMT. Here we need SMT because we have integers here, and without having integers, it would also not be so easy to encode this problem. So first of all, we have to say what the specification for the program looks like. So we have to declaratively say or describe how what the result should look like. And this is a manual process, and here the most effort goes in when we do some verification. So how can we describe the problem in terms of a logical formula? Now we can say, okay, we have an array, and the array has three positions. It has position I, position j, and position k. And at position I, the array should have the value of x. At position j, it should have the value of y. And at position k, it should have the value of z. So we have the three numbers in the array. Then we require that the array is sorted by saying that the value at position 0 is smaller or equal to the value at position 1, and the value at position 1 is smaller or equal than the value at position 2. And also we require that all values of the index variables are different. Yeah, so I is different to j, I is different to k, and j is different to k. And if these constraints are satisfied, then we know that the value m, which we are looking for, is at position 1. Yeah, and this is we have here. When these conditions here are true, then we know that that m has the right value. Yeah, and the important thing is also that assumption is that writing down the specification is much easier than writing down the program. Yeah, this is already quite a complicated specification. Often some properties are much smaller, which should be checked. Okay, and now we also need to translate the program into an SMT formula, and this is really easy because we do not have any loops, we do not have any complicated assignments, and what we can do is we can just translate the if-then-else statements according to the different branches we have here. If y is smaller than z and x is smaller than y, then m equals y. If y is smaller than z and x is larger or equal to y and z is smaller, x is smaller than z, then m is y, and so on. Yeah, so we translate all the different branches into the constraints we have here on the right hand side. And the nice thing is that this can be done completely automatic. So here really no thinking is necessary. We just can give this to a compiler and translate the program directly into an SMT representation. And the only thing that is left to do is to connect the representation of the program and the SMT representation of the specification. And how can we do this? This we can do by saying that the program is correct if the solution of a program is also a solution of the specification. So if P has a solution, then this solution is also a solution of S. So the implication P implies S is valid. SMT solvers do not check validity, but they check satisfiability of an SMT follower. This is like in SAT. So what can we do now? We can use this trick with the negation in order to transform the validity checking problem into a satisfiability checking problem. So we can say that a program has a bug if P implies S is invalid. Yeah, so P implies S has a counter model. This means the program has a bug if the negation of P implies S is satisfiable, because the counter model of P implies S is a model of the negation of P implies S. And if we now negate the formula, we obtain P and not S as a formula, and this formula we can check for satisfiability. So if we find a model for this formula P and not S, then we get an execution of P which is inconsistent with the specification. And now let's write this down as an SMT formula. So we have the SMT representation of P, we have the SMT representation of S, and we negate this, and here we have this. Here we can use this trick that we do not have to shift the negation completely inside and then swap everything, what we could also do, but what we simply do is we say M is different of A1. Yeah? This comes also because we have this, when we go back, we have here these constraints here imply M is equal to A1, and if we negate this, if you remember, disjunction can be, not a disjunction, an implication can be represented as in terms of a negation and disjunction. So if we have A implies B, then this is the same as not A or B, and so when we negate not A or B, then we get A or not B, and therefore we have only the negation here, and we have M is different to A1, and this we can now put or translate into SMT lib format, and we get this formula we have here, and this formula is now a bit more complicated as the formula we had for the magic square, because we have now arrays, and here we have the declaration of A, and for the array we have to say the type of the elements and the type of the index. Yeah, and for the other variables we have just integers as before, and then we have these assertions which directly come from the formula we have discussed before. And this now let's put this also into C3. I copied the program into the web interface of C3 and already pushed the execution button, and here I get the model. So unfortunately the formula is satisfiable. This means we have a bug in the program, and the problem is that or not the problem, but we get values for z, y, and x. Yeah, so we have now when we call middle, I'll write it down here as a comment. When we call middle with values, z is now if x is 2282, then y is 2281, and z is 2283. We have a test case which gives us the problem. This is not the smallest one, as we have seen before, but it's one which leads to a problem. And with this, we can now debug the problem, the program, and if let's see where we have the problem. If so, into which branch do we go? We have here y is smaller than z, so we're somewhere here, and x is larger than y, we're here, and x is smaller than z, so we're here, and obviously now the middle number should be x. Okay, and if we execute it now, then we get unsat, because there is now no solution to the middle problem which violates the specification. So we cannot execute, we cannot find an input for the middle program such that the specification is violated, and this is very good. Yeah, and in the following we will now have a look what SMT is actually about, and we will learn about the background, how the solving of such formulas work. So far we discussed propositional logic and learned about how to efficiently solve the decision problem of propositional logic, the SAT problem. The motivation to do so was that a lot of problems of practical relevance can be efficiently encoded into propositional formulas, and then the solution to the SAT problem gives the solution to the original problem. However, first of all, not all problems fit into the SAT framework. Some are harder on the one hand, and on the other hand, often the encodings become extremely complicated because in SAT we have only Boolean variables. So we have this powerful reasoning engines on the one hand, the SAT solvers. On the other hand, the language is not very expressive. Therefore, we looked at the other extreme, at first order logic, which is a very powerful language where we have a lot of concepts. We have quantifiers, we have terms, functions, variables, and in principle, this is a very, very, very rich modeling language. But the problem is that the reasoning becomes extremely expensive, and sometimes formulas cannot be decided. And in practice, often not the full power of first order logic is needed, but only a decision problem with respect to a certain theory, like integers, arrays, strings, bit vectors, and so on. And the non-standard interpretations are not of interest. So when we have a formula like the formula we have here, then we want to read the plus as a plus, the addition of two numbers. This symbol here is the smaller symbol. Yeah, the Boolean connectives stay the same. And the values, the variables should be restricted to a certain domain. Yeah, so we're not interested in arbitrary interpretations, but we want to have only those interpretations where x and y are, for example, integers and plus, and the comparison operators are interpreted as usual. So what we want to have is we want to have a restricted solver that is tailored towards the application we have in mind, and where we have efficient solvers for the theories that are needed. Yeah? So for example, we want to decide a set of integer inequalities with an efficient tool. And we do not require that the theories that are under consideration are themselves expressible in first order logic, but we can use specialized inference methods that are developed for each theory. And what we get when we do so is SMT, satisfiability modulo theory, which is a sweet spot between SAT and first order. So it's the compromise where we get enough expressiveness as required and as much efficiency as possible. And what we basically get is propositional logic plus domain-specific reasoning, and this gives us reasoning engines which in general are more efficient than general purpose solvers like first order solvers, which incorporate specific theory axioms. And here we have another example of an SMT formula. We have a conjunction of constraints, and the constraints are equalities, and here we have a disequality, and we have numbers. Here, for example, we have 3, and the symbol 3 we have here should be really interpreted as a 3, and we require that x plus u gives the value 3. So when we sum up those two variables, the values of the two variables, then we get 3. We have uninterpreted functions. Here the f is an uninterpreted function. It has arity 1, meaning it has one argument, x and y, and we require, because of this first constraint we have here, that fx is different from fy. Here we have an array with this notation that is common in many programming language. So we access the value of a at position z here, and this value should be equal to u, and so on. So we can have a very powerful language with a lot of concepts that help us to encode our problem. And in principle, what we have here are formulas in first order logic. Usually there are no quantifiers, and we assume that the variables are implicitly existentially quantified. So what we're going to solve with an SMT solver are decision problems of satisfiability. Yeah? So we want to know whether there is an assignment to the variable under which the formula evaluates to true. What we also have is that the symbols that we have in our formula are sorted, it means typed. So we know which kind of values can be assigned to x, can be assigned to u, and so on. And we have the possibility to interpret functions, constants, and predicates, except for the uninterpreted one. So for example, here this equality symbol is interpreted as equality. The plus here, the plus symbol is interpreted as addition. And what else? Here the constant 3 here is an example of an interpreted constant symbol. And this gives us a much richer language than we have in propositional logic and makes the reasoning much easier than it would be in first order logic. And satisfiability modular theory reasoning is extremely popular, not only in academia. So there is not only theoretical interest in this formula, but there are also many companies that use SMT formulas to solve various kinds of reasoning problems. This ranges from verification problems, as we have seen it before, with the simple example of the middle program, but also for scheduling problems. And for example, several sport leagues use SMT solvers to schedule their program. Yeah? And such things can be easily formulated in SMT formulas. And as we have already seen, there is this SMT-lib language, which is a standardized language that is used in many applications, which is supported by many solvers. So it makes the exchange between different tools very easy. And there is also a tool competition, the SMT competition, which is organized annually. And in this competition, different tools, different solvers are compared against each other. And as you can imagine, this is very challenging to organize such a competition, because this is different in SAT. In SAT, we have only one kind of formulas to focus on, or maybe some variants, like industrial problems or random problems, things like that. But in SMT, we have these different theories and these different features that are supported by the different solvers. And so the SMT competition is really, really huge and has a lot of tracks and also a lot of participants. And you can find more information about the SMT competition in the web. A bit about the historical backgrounds. Actually, SMT is rather old, so the idea to have a focused reasoning facilities and not exploit the full power of first order logic, which is maybe restrictive in some sense, dates back to the 1970s and 1980s. But back then there were neither the computers that were needed that are needed to execute solvers, and also back then there was also not the SAT technology that was the driver for successful SMT solver. SAT became very well understood and made a huge step forward in the 1990s. This comes from AI research. So there is the symbolic branch of artificial intelligence, which, for example, is concerned with planning. And in the 90s, it was figured out that SAT can be used very well for solving planning problems. And this went together with the invention of very powerful reasoning technology for SAT, which includes conflict-driven clause learning. And with this, SAT solvers became ready for large-scale applications. Yeah? And the reasoning on and solving of planning problems then inspired certain verification tasks, and these verification tasks were then again a driver for improving SAT solvers, because then there was a motivation why SAT solving, efficient SAT solvers are needed. Yeah? And therefore SAT solvers became better and better and better. And then with the improvement of the SAT solvers, it became also interesting again to have a look at this idea of SMT. And then there was the insight that SAT solving could be used actually to control and to also support the SMT solving. Yeah? And in principle, there are now two solving approaches for SMT. There is eager SMT solving and lazy SMT solving. In eager SMT solving, the SMT problem is translated to a propositional problem, and then this propositional problem is given to a SAT solver. There is maybe a huge blow-up, but for certain theories this works very well. We will also see some examples. And on the other hand, there is lazy SMT solving, and this is also something we will look at next week. This is very interesting. There we have the SMT formula, build a propositional abstraction. Yeah, we remove the predicates and replace them by propositional formulas. Give this abstraction to the SAT solver. The SAT solver says there is a solution for the abstraction. Then we map the solution of the SAT solver to a set of theory constraints, check if this set of theory constraints is consistent, and if yes, then we have a solution to the SMT problem. If this is not the case, so if the set of constraints is inconsistent, then the propositional abstraction is refined, again solved by the SAT solver, and either the formula becomes unsatisfiable, then it's clear that there is no solution to the SMT problem, or it's again satisfiable, and then the theory constraints have to be checked again. But this we will look at in detail next week. What I would like to do today for the remaining time is I would like to have a look at two background theories and show you how how the reasoning with this background theory works, and how a decision problem for the theories can be decided. The first theory I would like to show you is the theory on equality with uninterpreted functions, which is abbreviated EUF. And here we have functions as in first order logic, and the functions which we are considering are sorted, so they are typed, but they do not have any specific interpretation for the reasoning. Yeah? So the solver doesn't know what the function means, and this is an extremely powerful tool for abstraction, and we will see soon an example what we can do with these uninterpreted functions. And the only interpretable predicate we have in this theory is the equality symbol. And for the equality, we introduce the congruence axiom. So a theory is defined on the one hand based on the elements it talks about, and on the other hand we have some axioms which tells us the rules of the theory reasoning. And for equality we have the congruence axioms, and it says as the following: for all x, y, it holds if x equals y, then f of x is also f of y. Yeah? So when we know that x equals y, then the application of a function on the two variables leads to the same result. Yeah, important. It does not hold in the other direction. So let me switch to the writing. If we know, for example, that f(x) equals fy, then it does not necessarily follow that x equals y. Yeah, because fx could be, say, a, fy could be b, and a could be different than b. And with this, we have a perfectly satisfiable set of constraints. Yeah, but if we have a function, and if we have two variables which are known to be the same, so if we have, for example, x equals y, and we know that fx is a, and we know that fx is b, xy is b, sorry, then we can conclude that a equals b. Yeah? So from x equals y, it follows that fx equals fy, but it is not the case for the other direction. If we know that fx equals fy, we cannot conclude that x equals y. Yeah? Okay. So what can we do with these uninterpreted functions? Let us have a look at an example. They are extremely powerful to obtain abstractions from concrete realizations. Here I have an example. We have here this formula where we have uninterpreted symbols or functions f. Yeah, that's all. And we have interpreted symbols, multiplication and addition. Yeah, and we want to know if this set of constraints is satisfiable or if it's inconsistent. And what we now can do is we can replace multiplication and addition by an uninterpreted function. So we build an abstraction of the formula, and what we get is we simply replace the multiplication by h, and we get HAF. HA, and the plus we replace by G. So as the second argument, we get GFB and GFB-FC. This comes from the plus here. This equals to D, and then here we have the H for this multiplication here, and here we have the G for this plus here, and get HB, GFA, GFC, and AB. And now when we look at this abstracted formula, where we do not talk about plus and multiplication, what can we conclude? We suddenly have, when we use the congruence axiom, we know that, no, we do not need the congruence axiom. First of all, we know that A equals B, so we could, for example, replace the B here with an A. I haven't written it down. So we can replace the B here with an A. And what else can we do? We can also replace the B here with an A. Yeah, then we have twice the same formula here. One time it is T, the otherwise it is not T, and therefore we can conclude that this set of constraint is inconsistent. Maybe let me write it down again to ensure that it's clear what I just did. When we look at this formula, we see that A equals B, as we have here, and therefore we wouldn't change anything if we replace all occurrences of B by an A. So what we get, let's write it down in black, H of A, G, F, A, F, C is the same as D, and H, A, G, F, A, F, C is different from D. And when we now look at the two expressions with the H, we see that they are the same. Yeah, so this is equal. And now we have a problem, because one time this H expression is equal to D, one time it's different to D, and therefore we have a contradiction. Yeah, and since now the abstraction is unsatisfiable, we can also conclude that the original formula is unsatisfiable, because here this original formula gives less interpretations that could be has less interpretations that could be models, and therefore if already this more relaxed or this abstraction is already unsatisfiable, then also the concrete formula has to be unsatisfiable. And with this we can decide without using any specific reasoning on integers. And however, if the abstracted formulas was satisfiable, then we could not conclude anything about the original formula. And next I will show you an algorithm to decide efficiently whether a set of constraints with equality is consistent or not. And what we do is we first put all terms and subterms into different equivalence classes. So we have equivalence classes of size 1. And if we have an equality, we merge the two equivalence classes of the two terms. And for the equivalence check, we also consider the congruence axiom. And if there are terms T1 and T2, we also consider terms Ft1 and Ft2. And then if they are equal, Ft1 and Ft2, we merge their equivalence classes as well. And we continue until no further merging of equivalence classes is possible. And if we have a disequality, saying that T1 is different to T1, and T1 and T2 are in the same equivalence class, then we can decide that the set of constraint is unsatisfiable. Here I have an example. In our example, we assume that we have a flattened structure, so we have no nestings, and all subterms are identified by variables. Yeah? If we have this structure where here we have an x, and on the other side we have the function, here we have a t, then here we have a function, and so on. If we have the structure, then it's enough to put the variables into the equivalence classes. So we have the equivalence classes with the x, the y, the t, the u, and the v. And now we use the equalities to refine the equivalence classes. Here we have x equals y, therefore we merge the class of x and y and get xy. Then here we have x is equal to gy and t is equal to gx. We already said that x equals y, therefore we can replace the x or the y by the other one, and we can conclude that x is equal to t, and therefore we merge the two classes and get a class containing x, y, t. Good. Then in the next step we look at these two equations. We have u is equal to fxt and v is equal to fyx. And if we now apply the congruence axiom, then we can conclude that u and v are the same. Yeah, and we get this partition here, and now we have this disequality. U is different than v, and therefore we can conclude that this set of constraint is unsatisfiable because u and v are in the same class, but this constraint here states that they should be different. And with this we have a very efficient algorithm for deciding the satisfiability of constraints with uninterpreted functions and equality, and there are also very efficient data structures to implement this. The other theory I would like to discuss with you is the theory of linear real arithmetic, LRA, and what we have in this theory are integers, rationals, etc. We have predicates equality, disequality, inequality, strict inequality, etc. We have addition, subtraction, multiplication, and so on. But the multiplication is restricted that in the sense that we can multiply by constants only. So as we have it here, for example, because otherwise we would not have a linear real arithmetic, but just arithmetic. And we focus on conjunction of inequalities, as we have it here. And equalities can be replaced by two inequalities always, so we do not treat them specially. And exactly, and we consider only conjunctions because if we have other connectives, other logical connectives, this could be handled with a SAT solver. This we will see next week, how to do this. And being able to solve such set of constraints is very important in the context of solving optimization problems, as they're solved in operations research, where you want to find a good solution for some optimization problem. And a very famous algorithm for solving this problem is the Simplex algorithm, but I will now show you the very easy Fourier-Motzkin elimination procedure for solving this kind of reasoning problem. So we have here this set of inequalities, and what we do first is we pick a pivot variable, say we pick x, and isolate it on one side such that we have it there with coefficient 1. Yeah. So what do we have to do? We put here the y on the other side and get z plus y smaller equal than x. Here we put the 2 times y on the other side, and here we put the 2 times x on the other side, and there we have to take care of the 2. We divide it and get 2 times z minus 0.5 times y is larger or equal than x, and in order to get the x on the other side, we simply switch this larger equal than to a smaller equal than. Yeah? And then we have this representation where we have only smaller equal than equalities. And now we eliminate the x by adding new inequalities for the following. So if we have a is smaller or equal to b, if we have a is smaller or equal to x and x is smaller or equal to b, then we add inequality a is smaller or equal to b. Yeah. And this we do here. So we get z plus y is smaller or equal to 5 minus 2 times y. Z plus y is smaller equal to this expression here, and then we are already done because we have these two new inequalities. And what we do next is we pick another pivot variable. In this case we pick z and transform the inequalities, and then we eliminate z, and finally we have only the inequality with the y, and with this we can find a solution for the y. Often there are many, but we pick one, and then we see if and then we propagate and pick a solution for the z, and then we get a solution for the x. And with this we have a solution which satisfies these constraints what we have up here, and therefore we can conclude that this set of constraints is satisfiable. Yeah? I did not formally introduce this algorithm, but I hope the idea is clear. What we basically do is something very similar to resolution, where we have the pivot element, positive literal, negative literal, and we combine the rest of the clauses, obtain a new clause, and eliminate the pivot literal. Something very similar we do here, and with this we can decide this kind of sets of inequalities. Yeah, and if we want to have more Boolean connectives, we need a SAT solver, and this I will tell you next time, how we can have disjunction, negation, and so on in an SMT solver, and I will show you how a SAT solver can help here. Thank you very much for watching.